All right, we're going to begin this particular review by starting with the discussion of the temperature field. What we're going to be looking for is the derivation of the heat equation. So the temperature field is going to be obtained by applying conservation of energy, in this case thermal energy, to a designated and appropriate control volume. So the control volume for a Cartesian three-dimensional system will be different than the control volume for a cylindrical system. So once we're doing this, we also have to think about specific options. We know we're going to have energy transfer due to conduction, but we can also develop the heat equation for the case where we would have internal heat generation designated by Q dot, and we can also look at or allow for a time-dependent change in the amount of stored energy within the volume. And we would give this term equal to the density times the specific heat at constant pressure times the derivative of the temperature field with respect to time. So obviously this is a time-dependent term which will be zero for steady state conditions, which is what we've looked at up till now. So making a quick graphic of the situation here, we have a control volume arbitrarily shaped, and we have an energy input term and an energy output term, both rate equations, and inside the control volume we have E dot gen and E dot st for generated energy and stored energy, both as time dependent or rate equations. So this is going to allow us, this graphic allows us to write the energy equation or conservation of energy in terms of these particular quantities. And to actually put into what we're going to be utilizing, we're going to have a value for Qn, the rate of energy transfer into the control volume, the rate of energy transferring out of the control volume, the rate of energy generated within the control volume, which would be watts per cubic meter, times the control volume, times the volume of the control volume. And same thing over here. The change in energy stored, these three terms, will also be times the volume of the control volume. So if we look at a specific example, this will be a 1D Cartesian example. So then again, this is our specific control volume now. So it's really, we only have a coordinate in the x direction. We can assume this volume is infinite in the y direction and infinite into the paper here in the z direction. So we're going to allow for energy to come in, and again by conduction. So this will be Fourier's equation, and it's also going to leave, and the rate of energy leaving will be modified by the functionality that we're looking for, right? We're looking for temperature as a function of x, and it's going to change slightly in between the coordinate x and this differential element x plus dx. We're also going to allow for or take into account that the energy generation term in this case will be zero for this example, as well as we'll make it steady state, so the stored energy term will equal zero. Now, if we look at what's left, we only have the two conduction terms, Qx and Qx plus dx. Now, to the Qx plus dx term, we've looked at it in class, and it's essentially, it's a Taylor expansion, or think of it as just a straight line, which is the case here. The change or the difference in the energy rate term is going to be what it was at x plus essentially the slope of the functionality of q as a function of x times the delta function, or times dx. So it's basically mx plus b. That's essentially the equation of a straight line. So once we apply that, or essentially simplify this function, the qx terms cancel out, and we're just left with this differential term. So let's take a look at it. So here's the functional term of q with respect to x times, now this is an actual number, shall we say. This is the distance that we're looking at. So the dx term is physically this value, which we're going to consider a constant in our analysis. So to get the value for q, we're going to apply Fourier's law, which we've just developed, and in doing this, we can now write Fourier's law in for the value of q. So we've substituted this equation here for q, giving us this. Now, k is a constant, the area is a constant, and as I said, this dx term is also a constant. So taking our constants and pulling them outside the differential, we are left with this. Now here I've taken the area term and I've explicitly wrote them in terms of a differential, in this case dy times dz, just to let us know that we are again dealing with a differential control volume. Well, anyway, this entire term is a constant, so we can divide it through by it, and that leaves us with the one-dimensional heat equation, which is this term here. So it's ddx of the derivative with respect to x of the temperature field, and all that equals 0. So again, taking the derivative of anything, and if it equals 0, that means the thing that you've taken the derivative of must be a constant. So dt dx equals a constant, and that applies that the function is going to have constant slope, meaning that what we're essentially looking for, the variation in the temperature field as it moves from one side to the other side, is going to be, as we expect, a straight line, and the straight line has constant slope. So that's the derivation of the heat equation for 1D Cartesian coordinate system.